So in the last video, we talked about how we could take a given state of stress with the two normal stresses, sigma x and sigma y, and a shear stress, tau xy, and we could find the principal stresses, sigma p1 and sigma p2, which were our we can use an eigenvalue problem to solve for those two, sigma p1 and sigma p2. And then using our eigenvalues, we can define our eigenvectors. So we defined our eigenvectors. We had two different eigenvectors. We had an eigenvector v1 and we had an eigenvector v2, corresponding to the first and second principal stress. So at the very end of that video, we talked about how we can correlate our eigenvectors to the directional cosines theta p1 and theta p2. So the angle between our first principal stress and our second principal stress with the x and y axes is essentially what we're getting at here. So what we can do now is we can using the relationship between sines and cosines is that we can say that since the sine of 90 minus theta, since this sine of 90 minus theta is the same thing as cosine of theta. All right, using this trigonometric identity, we can replace our two sine terms. Our two sine terms in our eigenvectors here with cosines. Okay, using this identity. Okay, so all right, so using like the inverse cosine function on your calculator, you can actually determine the angles between our principal axis, which is our first principal axis, we'll denote as axis 1, and the x-axis, and our first principal axis 1 and the y-axis, and theta principal axis 2, x, and our and theta principal axis 2y. All right, if we do that, what we end up getting is we get these values: 63.4 degrees, 26.6 degrees, 130, 150, 3.6 degrees, and 64.4 degrees. All right. So the question we have here is we originally had our XY coordinate system, okay, and the question is how do we rotate it? Do we rotate it clockwise or do we rotate it counterclockwise to get our new state of stress? So we're basically asking, is it x prime, x prime, y prime look like this, or does it look like this? Okay. So basically, is it a counterclockwise rotation or is it a clockwise rotation? Now remember, these are our given angles that we were given. So theta 1x here represents the angle between our first principal axis, theta 1, our first principal axis, and our x-axis. So this would be theta 1x, okay? And then theta 1y represents the angle between our first principal axis and um, uh, uh, and the original y-axis. So this is representative of theta 1y here. So as you can see, um, for theta 1y and theta 1x to verge on the same principal axis, axis 1, the first principal axis needed to be in like the fourth quadrant of our coordinate, our original xy coordinate system. Okay, or you can think of it as the element needs to be rotated clockwise 64.3 or 64.3 degrees. Well, what you notice is if you try to rotate it counterclockwise, 64.3 degrees, and you try to find the angle between the first principal axis and the original y-axis, theta 1y, is that it would actually go along not the positive x-axis or one axis, it would go along the negative one axis. So because these two angles do not meet, that's not the proper coordinate system, and it wouldn't create a proper transformation. So that's why the coordinate system on the right-hand side is the correct coordinate system. So after all this work from our example problem, what our final stress element looks like is the following. Okay, so we started off with our original state of stress, where we had our normal stresses sigma x, sigma y, and tau xy. And after doing our principal stress calculations, we calculated our two principal stresses, sigma p1 and sigma p2, as well as our angle of rotation, theta 1x here. Okay? All right. So that concludes how you can perform stress transformation using eigenvalue and eigenvector formulation. The additional thing I do want to point out here is that if you go to the um, equations page, what you'll notice is that you can use algebraic. You can solve these types of problems in plane stress relatively easily using these two algebraic equations, where you can solve for sigma p directly, and you can also solve for theta directly using these two types of using these two algebraic equations. So you're more than welcome to use that equation as well. Just because this is a more advanced course, I wanted to show you the eigenvalue and eigenvector formulation, because it's especially more applicable when you start using computers to help solve these problems, and when you are doing 3D matrices, which we'll be doing in upcoming lectures.